Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Here is Mubashir Riaz. Today we are going to discuss short questions and numerical problems of chapter number 14, Electromagnetism. शॉर्ट क्वेश्चंस और न्यूमेरिकल प्रॉब्लम्स को अटेम्प्ट करने के लिए आपके सामने टेक्स्ट बुक होनी चाहिए. So question number 1 is a plane conducting loop is located in a uniform magnetic field which is directed along x-axis. So for what orientation its magnetic flux is maximum and for what orientation magnetic flux is minimum. तो हमें मैक्सिमम और मिनिमम मैग्नेटिक फ्लक्स के लिए ओरिएंटेशन को डिस्कस करना है कि प्लेन कंडक्टिंग लूप की ओरिएंटेशन क्या होनी चाहिए. फॉर दिस पर्पस, in case of maximum magnetic flux, if plane of conducting loop is held perpendicular to field lines, then flux is maximum. If plane of conducting loop is held perpendicular to field lines, then flux is maximum, like this one. This plane is held perpendicular to those field lines, so flux is maximum. Maximum lines can pass through it, so there is maximum flux, which can be proved by mathematical phi b, which is equal to b dot a, and we know that b a cos 0, because field lines and vector area, they are along the same line, hence angle between them is 0, so maximum flux, which is equal to ba. Similarly, for minimum magnetic flux, this plane of a conducting loop should be held parallel to field lines. So there should be a word parallel to field lines, then flux is minimum, like this. So in such case, no line can pass through that plane. So flux is minimum, and it can be proved mathematically. Phi b, which is equal to b dot a, ba cos 90, and cos 90 is equal to 0, so flux is minimum. So this is question number 1 for maximum and minimum flux. Question number 2. Current in a conductor produces a magnetic field which can be calculated using Ampere's law, since current is the rate of flow of charges. So what can you say about the stationary charges? यानी अगर एक कंडक्टर में से करंट पास होता है तो उसके इर्द गिर्द मैग्नेटिक फील्ड पैदा होती है, और करंट जो है वो रेट ऑफ फ्लो ऑफ चार्ज का नाम है. क्या स्टेशनरी चार्जेस से भी मैग्नेटिक फील्ड पैदा हो सकती है? सिंस करंट इज द रेट ऑफ फ्लो ऑफ चार्ज, and when current passes through the conductor, magnetic field is produced around it. यानी मैग्नेटिक फील्ड के प्रोड्यूस होने के लिए करंट का कंडक्टर में से पास होना जरूरी है, एंड करंट इज द रेट ऑफ फ्लो ऑफ चार्जेस. हेंस we can say that magnetic field cannot be produced by the stationary charges because they are not in state of motion, they are in state of rest, so they cannot produce magnetic field. So this is question number 2. Question number 3. What is the effect on the magnetic field inside a current carrying solenoid if length of the magnetic field is doubled by keeping the number of turns constant? कि अगर हम सोलिनॉइड की लेंथ को डबल कर देते हैं लेकिन नंबर ऑफ टर्न्स को चेंज नहीं होने देते, तो इससे मैग्नेटिक फील्ड पे क्या फर्क पड़ेगा? एंड इफ नंबर ऑफ टर्न्स आर डबल but length remains the same, so in both cases we have to discuss the effect of on the magnetic field inside a current carrying solenoid. So with respect to length, since we know that magnetic field inside the current carrying solenoid can be determined by using Ampere's law, by using this mathematical form, B is equal to mu naught Ni, where small n can be replaced by n over L. Small n is n over L. According to condition, if length becomes double, this is the condition, if length becomes double, then what will happen to the magnetic field? So by putting this condition, B prime becomes equal to mu naught n over 2L into I. So 1 over 2 into mu naught n over L into I, and this one is equal to actual magnetic field B. So B prime is half B. Hence we can say that by doubling the length of solenoid, magnetic field reduces to half. And what happened to the magnetic field when number of turns are double? So here B is equal to mu naught Ni, where small n replaced by n over L, and this is the condition. If number of turns are double, but the length remains same. So in this case, magnetic field mu naught 2n over L into I. So 2 into mu naught n over L into I. So B prime becomes equal to 2 times of the actual magnetic field. So this is the result. Hence, by doubling the number of turns, magnetic field also becomes double. But by doubling the length of solenoid, magnetic field reduces to half. यानी अगर solenoid की length को double करेंगे तो magnetic field पहले से भी कम हो जाएगी. लेकिन अगर number of turns को double कर देंगे, then magnetic field also becomes double. So this is question number 3. Question number 4. A proton moves in the positive x direction in a region where there is magnetic field in the negative z direction. यहाँ आपने याद रखना है कि proton is a positively charged particle and it is moving along positive x-axis, whereas magnetic field is directed along negative z-axis. So what is the direction of magnetic force experienced by the charged particle? यानी उस particle पे act होने वाली magnetic force की direction क्या होगी? Will the proton continue to move in the same direction under the action of magnetic force? So here proton is moving along x-axis, whereas a uniform magnetic field is applied perpendicular to its motion along negative z-axis. Since we know that when charged particle moves through a uniform magnetic field, it always experiences a magnetic force, which is Fb equal to Q into V cross B. So this is magnetic force experienced by the charged particle. Under the action of this magnetic force, according to right-hand rule, if we rotate velocity towards the magnetic field, and velocity is along x-axis and magnetic field is directed along negative z-axis into the plane. So if we rotate V towards B with the help of right hand, then force is directed along positive y-axis. So this is direction of magnetic force experienced by the particle along y-axis. And this force is perpendicular to the motion of charged particle. So it will change the straight line path of that charged particle into curved path, and this particle will not continue to move along straight line. यानी इस force के तहत ये particle कभी भी अपनी straight line motion को maintain नहीं रख पाएगा. ये force उसके straight line path को curved path में change कर देगी. So this is question number 14.4. Question number fifth. Two charged particles are projected into a region. इस क्वेश्चन में ये कहा जा रहा है कि there are two charged particles and they are moving through a region where there is a uniform magnetic field perpendicular to their motion. यानी वहाँ ऑलरेडी मैग्नेटिक फील्ड मौजूद है और वो उन पार्टिकल्स की मोशन के परपेंडिकुलर है. So if they move in different path after passing through that uniform magnetic field, then what can you say about those charges? So this is the situation. There are two charged particles, electron, positron, and proton, and they are moving perpendicular to this this magnetic field. So what can you say about the charges? So when they move through this uniform magnetic field and they gain different path, if they move in opposite direction, then we can say that they have opposite charge on them. इनमें से एक इलेक्ट्रॉन हो सकता है और दूसरा प्रोटॉन हो सकता है. That's why they move into different directions to opposite direction. So this is the answer. They are of opposite charge. One of them is positive and the other one is the negative charge. Question number 6. Why there is no work done by the magnetic force? कि एक चार्ज पार्टिकल जिस पे चार्ज Q है, जिसका मास M है और वो मैग्नेटिक फील्ड में दाखिल होता है, मैग्नेटिक फोर्स एक्सपीरियंस करता है, लेकिन वो मैग्नेटिक फोर्स वर्क परफॉर्म क्यों नहीं करती? Why there is no work done by the magnetic force? So its answer is when charged particles move through a uniform magnetic field, then it tends to move in a circular path under the action of magnetic force. So when particle is moving in a circular path, its direction of motion is always along tangent. That is displacement. That is always along tangent. And magnetic force experienced by the charged particle is directed towards the center of circle along the radius. So angle between force and displacement becomes 90 degree. This is the angle which becomes equal to 90 degree between them, and due to this 90 degree angle, work done becomes equal to 0 because we know that FD cos 90 is 0. So this is the answer of question number 14.6. Question number 7. A charged particle enters through the given region of space and it moves along the straight line. एक चार्ज पार्टिकल एक गिवन रीजन ऑफ स्पेस में एंटर होता है और वो स्ट्रेट लाइन के अलोंग मूव करता है. तो क्या इसका ये मतलब होगा कि वहां मैग्नेटिक फील्ड 0 है और एनी अदर पॉसिबिलिटी? So this is the statement. If a charged particle moves straight through some region of space, then there are two possibilities. कि अगर एक चार्ज पार्टिकल किसी स्पेसिफिक रीजन में से स्ट्रेट मूव कर रहा है, now there are two possibilities. Possibility number 1, magnetic field in that region is 0. If magnetic field is 0, B is 0, then according to the above equation, which is QVB sine theta, magnetic force also becomes 0. So this is first possibility. In that given region of space, magnetic field is 0. And the other possibility is magnetic field is present, but it is parallel or anti-parallel to the motion of charge particle. So if it is parallel, then angle between V and B is 0. If it is anti-parallel, then angle between V and B is 180. So in both cases, sine 0 as well as sine 180 is also equal to 0. So magnetic force becomes 0 and the particle moves along the straight line without any deflection. अगर magnetic field present हो और perpendicular हो, तब इसका straight line path curved path में change हो सकता है. But if it is parallel or anti-parallel, then it will not experience any kind of force and particle moves along the straight line. Question number 8. Why does the picture on a TV screen becomes distorted when a magnet is brought near the TV screen? कि जब आप एक टीवी स्क्रीन की करीब मैग्नेट को लेके आते हैं तो उस पे मौजूद पिक्चर डिस्टॉर्ट क्यों हो जाती है? So why it distort? So remember this picture on a TV screen is formed by beam of electrons. जैसा CRO में हमने पढ़ा कि when electrons move towards the fluorescent screen, they produce visible spot on the screen. Similarly, in case of TV's picture is formed by the beam of electrons and they also produce magnetic field. those electrons, they also producing magnetic field on the screen. So when another magnet is brought near the TV screen, आप किसी सेकंड मैग्नेट को टीवी स्क्रीन के करीब लेके आते हैं तो ये दोनों मैग्नेटिक फील्ड्स इंटरएक्ट होंगे. वन इज द मैग्नेटिक फील्ड प्रोड्यूस्ड बाय इलेक्ट्रॉन्स and other magnetic field is producing by the magnet. They interact with each other. That's why the picture on TV screen becomes distorted. Question number 9. Is it possible to orient a current carrying loop in a uniform magnetic field such that the loop will not tend to rotate? क्या ऐसा मुमकिन है कि एक करंट कैरिंग लूप को मैग्नेटिक फील्ड में रखा जाए और ये फिर भी रोटेट ना हो? So yes, it is possible. It is possible by placing the current carrying loop in the uniform magnetic field and it does not rotate. For this purpose, the plane of current carrying loop, याद रखना है plane होना चाहिए. So when plane of current carrying loop is held perpendicular to the magnetic field, then it does not rotate. If plane of current carrying loop is held perpendicular to field lines, then it does not rotate, because we know that tau is equal to BINA cos alpha. If angle between plane and the magnetic field is 90 degree, then it becomes 0. So in such case, torque is equal to 0. So plane of current carrying loop is held perpendicular, then it does not rotate. Question number 10. How can a current loop be used to determine the presence of magnetic field in the given region of space? कि आपको एक specific region given है और आपने ये determine करना है कि क्या वहाँ magnetic field मौजूद है या नहीं, और इसके लिए आपके पास जो available apparatus है, that is only a current carrying loop. So with the help of that current carrying loop, we have to determine the presence of magnetic field in the given region of space. So it is very simple. By placing that current carrying loop in the given region, if it tends to rotate, then magnetic field is present. और अगर ये करंट कैरिंग लूप उस गिवन रीजन ऑफ स्पेस में प्लेस करने के बाद भी रोटेट ना हो तो फिर मैग्नेटिक फील्ड वहां 0 होगी. But if magnetic field is present, then current carrying loop will rotate. Last question according to smart syllabus 14.11. How can you use a magnetic field to separate isotopes of chemical element? एक केमिकल एलिमेंट के आइसोटोप्स को सेपरेट करने के लिए हम मैग्नेटिक फील्ड की हेल्प कैसे ले सकते हैं? हाउ मैग्नेटिक फील्ड कैन बी यूज्ड टू सेपरेट द आइसोटोप्स ऑफ अ केमिकल एलिमेंट. सो हियर इज isotopes are actually the atoms of an element which have same atomic number but different mass number. Since they have same atomic number, so they cannot be differentiate on the base of their chemical properties. They only can be differentiate by using their physical properties due to their different mass number. आप इनको इनके mass number की base पर separate कर सकते हैं. So इसी property को use करते हुए magnetic field की help से आप isotopes को separate करेंगे. So when such particles are projected into a region where a uniform magnetic field is present, they experience magnetic force, and under the action of magnetic force they tend to move in circular path of different radii according to their masses. यानी ये magnetic force experience करेंगे और उस magnetic force को experience करते ही ये मुख्तलिफ सर्कुलर पाथ में मूव करना शुरू कर देंगे और इनके जो सर्कल का रेडियस होगा वो इनके मास पे डिपेंड करता है. It can be proved mathematically by using this mathematical form. charge to mass ratio, E over m is equal to V over BR, where V is the velocity of those particles, B is the strength of magnetic field applied, and R is the radius of circular path. And from this equation, we can determine R is equal to mv over EB. And from this mathematical form, the relationship between R and mass, R is proportional to mass. So by using this concept, we can differentiate the atoms of an element which have different mass number. So these are short questions of chapter number 14. Now, numericals of chapter number 14. Numerical number 1. Find the value of magnetic field that will cause a maximum force on 20 centimeter straight wire carrying a current of 10 amperes. So according to statement, there is a piece of wire of length 20 centimeter equal to 0.20 meter, and current passing through that wire is 10 ampere. So find the magnetic field to produce the maximum force. Magnetic field आपने find करनी है to produce this maximum amount of force on this current carrying wire. We know that F is equal to ILB sine alpha, and from this mathematical form, B becomes equal to F over IL sine alpha. So by putting their values, where F is 7 into 10 is for minus 3 Newton, current is 10 ampere, length is 0.20 meter, and for maximum force, this angle should be equal to 90 degree. Then the strength of magnetic field required for this purpose is 3.5 into 10 is for minus 3 Tesla. So this is the strength of magnetic field required to produce the maximum force. Numerical number 2. How fast must a proton move in a magnetic field such that magnetic force is equal to its weight? There is a particle having charge 1.6 10 is per minus 19 coulomb, and the strength of magnetic field is 2.50 10 is per minus 3 Tesla. So how fast must the proton move through this given uniform magnetic field? हमें इसकी velocity find करनी है. And according to condition, the magnetic force experienced by the charged particle is equal to its weight. हमें इस condition को इस्तेमाल में लाना है कि इस particle पर act होने वाली force और इस particle का weight, they are equal to each other. So magnetic force is equal to weight, and we know that magnetic force is equal to QVB and weight is mg, and from this equation V becomes equal to mg over QB, where m is the mass of proton, और ये ज़बानी याद रखना पड़ेगा, 1.67 10 is for minus 27 kg. G is 9.8 meters per second square. Charge on the particle is 1.6 10 is per minus 19, and strength of magnetic field is also given. So the velocity of this particle would be 4.09 10 is per minus 5 meters per second. So this is the velocity of particle. Number 3, a velocity selector, it is also known as an accelerator, has a magnetic field of 0.30 Tesla. If a perpendicular electric field of 10,000 volt per meter is also present, so what will be the speed of particle that passes through the selector? Electric field is given, magnetic field is also given, so find the velocity of particle moving through this selector. अपने particle की velocity को find करना है. So this is the principle. FB, which is magnetic force, should be equal to the electric force, and FB is equal to QVB, जहां आप Q को Q से cancel कर सकते हैं. So they cancel out. Hence, the velocity of this particle is equal to E over B. So E, which is 10,000, B, which is 0.30 Tesla, So the velocity of that particle is 3.3 10 is power 4 meters per second. So this is the velocity of given particle in the given region of uniform electric field and magnetic field. Question number 4. There is a coil having area 0.1 meter into 0.1 meter. This is area of coil. Having number of turns 200 and current passing through that coil is 1 milliampere, placed in a uniform magnetic field 0.1 Tesla. So find the torque produced in that coil. आपने उस coil में produce होने वाले torque को calculate करना है. We know that the maximum torque is BINA cos BINA. This is maximum because cos 0 is equal to 1. So here, by putting all the values B, I, N, and A, the torque produces in the coil is 2 into 10 is per minus 4 Newton meter. So this is the value of torque produced in the coil. Problem 5. There is a power line 10 meter high, and this height of power line can also be written as the radius because this is in the form of a circle. So the height of this power line can also be represented by the radius, that is 10 meter, carries a current of 200 ampere. So find the magnetic field of wire at the ground. आपने ground पे magnetic field की value को find करना है. For this purpose we will take the help of Ampere's law, B into 2 pi r. यहाँ आपने याद रखना है कि जब हम mathematical form Ampere's law की पढ़ रहे थे तो वहाँ delta L लिखा था. Delta L was the length of a small element. लेकिन यहाँ हमें पूरी power line को discuss करना है तो हमें circumference उसका use करना है, that is 2 pi r and is equal to mu naught I. So B becomes equal to mu naught I over 2 pi r. So by putting their values, the strength of magnetic field produced at the ground is equal to 4 into 10 is power minus 6 Tesla. So this is the value of magnetic field present at the ground due to that current carrying loop of wire. Question number 6. You are asked to design a solenoid that will give a magnetic field of 0.10 Tesla. क्या आपको कहा जाता है कि एक solenoid डिजाइन करें जो कि 0.10 Tesla magnetic field produce कर सकता हो. Yet the current must not exceed, लेकिन साथ लिमिट बताई गई है कि करंट 10 एम्पेयर से ज्यादा नहीं होना चाहिए. So find the number of turns per unit length that the solenoid should have. तो इसके लिए आपने याद रखना है कि नंबर ऑफ टर्न्स पर यूनिट लेंथ कितने रिक्वायर्ड होंगे to produce this amount of magnetic field. So by using B is equal to mu naught Ni, where small n is number of turns per unit length and is equal to B over mu naught I, where mu naught is permeability of free space, whose value is 4 pi 10 is per minus 7, B is 0.10, current is 10 ampere. So the number of turns required for this purpose 796. यानी 796 turns per meter required होंगे to produce this strength of magnetic field. 796 number of turns. And the last question, 7. What current should pass through a solenoid that is 0.5 meter long with 10,000 turns of copper wire so that it will have a magnetic field of 0.4 Tesla? This is the length of solenoid, 0.5 meter. The strength of magnetic field 0.4 Tesla. Number of turns are 10,000. So how much amount of current is required to produce this value of magnetic field? आपने इसमें करंट मालूम करना है कि 0.4 टेस्ला मैग्नेटिक फील्ड पैदा करने के लिए करंट कितना चाहिए होगा. अगेन बाय यूजिंग द सेम मैथमेटिकल फॉर्म B is equal to mu naught Ni, where N can be replaced by number of turns per unit length. So here I becomes equal to BL over mu naught N. By putting their values, the amount of current required for this purpose is equal to 16 ampere. Sorry, there should be current I. This is a mistake. There should be current I, and it should be equal to 16 ampere. Thank you.